This next session is full of energy. Frossie and Angelo are super amazing. We're really fortunate to be able to have them speak today because we heard from Kirk yesterday about how they're doing infrastructure monitoring. A lot of you are monitoring your applications. We also have a bunch of IoT use cases, but they actually do that and more. And they actually, well, I'm not going to tell you exactly what they're actually monitoring. I'm going to leave that up to them. I'm not going to steal their entire thunder. But I do want to say that they've been really good friends. We've known Angelo for quite some time. We met Frostie just recently. And we've also met a number of the other staff members at the Flux training we had last month. And so we're really excited to see where they can push the limits of InfluxDB and Flux. And so today, Frossie and Angelo, if you want to share, I'd like to hand it over to the team at the Vera C Rubin Observatory.
Hi, we are very excited to be here. Can you hear me and watch the slide and see the slide share?
It looks beautiful and we hear you just perfectly.
All right, thank you. So we're excited to be virtually here to tell you about our project and the ways in which InfluxDB and the Influx team is helping us in our quest to make the deepest, widest map of the universe. We work for Vera C Rubin Observatory, which is building a telescope that is under construction that will perform the legacy survey of space and time. And we are part of a very small 7-person team that builds services for both internal users, the facility staff, and the scientific community. So, as we just heard, you know, we meet a lot of people who are very happily using Influx for DevOps and IT type metric use cases, and it's wonderful, and we use it for that as well. But we're here to kind of highlight two kind of less frequent users of this technology. And one of them is that we use Influx for capturing high frequency hardware telemetry from our advanced scientific instrumentation facility. And we also use Influx to capture scientific insight about our data streams. Both in an attempt to give your brain a little bit of a rest from all the hard work you've done this morning, and also to provide some context on our architectural choices and solutions, I'd like to tell you a little bit about how we got here. And it starts with space. And apologies to the Influx design team, but space is black. So we're gonna go deep now into the depths of space. And traditionally, the experience of observing the universe has been quite static in astronomy. But in fact, the universe is not static. Space is in a state of flux. See what I did there? And there are a lot of variable events, transit events that happen in every physical scale of the universe. You know, we're all very familiar with, you know, comets and asteroids that come whizzing through the solar system. Hopefully none of them will end us. But, you know, they vary in position, they move very fast across the sky. We have a number of stellar sources that are either catastrophically or periodically variable in their brightness, and they are very useful for us to probe certain fundamental physical questions about the universe. Thanks to the fact that the speed of light is finite, when we look further back, further away in space, we're also looking further back in time, and we were able to actually capture the stages of galaxy evolution. As galaxies get younger and younger, the further you look. And then there's the mysterious phenomenon of dark energy, which may vary or may not. We can't tell. If we knew, we'd get a Nobel Prize. But this is one of the missions of this telescope, is to try and probe our understanding of this phenomenon. For people like me who, you know, are up to date with the latest astronomical research, dark energy is a missing energy balance that we need to explain the fact that the universe is actually, that the universe's expansion is accelerating. And it is a matter of great theoretical debate, whether it is a constant energy or whether it's some kind of scalar field or vector field. This is one of the great cosmological open questions in astronomy right now. So we want to grasp with this changing universe and all these scales from comets and asteroids to the beginning of the universe. The rest of this little presentation I'm going to give you will tell you how to understand this in 5 not so easy steps. And not included in the 5 steps is step 1, find funding. We are funded by a mixture of sources. Charles and Liz Monifan gave us a very generous donation early on that allowed us to construct our mirror. But the majority of our funding comes from the National Science Foundation and the US Department of Energy. And therefore, if you're a US taxpayer, we thank you. Your money supports science and our scientific endeavors. Right, so step 1, you need a big camera. On the left picture here, there's a person for size to show you the image of our lens of our camera. And on the right in the video, what you see is the filter mechanism being exercised in the laboratory where the camera is. This is a 3.2 gigapixel camera. It consists of 109 science grade CCDs and an additional 4 wavefront sensing CCDs. The CCDs are 4K by 4K, so they're very large CCDs to start with. And in fact, we needed so many science grade CCDs that we actually were unable to get them from a single manufacturer. So we had to go to 2 to make enough to fill our focal plane. Moreover, what you see here moving down is one of 6 filters that we use to take observations in different parts of the color space. As you can see, the filters are also quite ginormous. And what you see here is the shutter assembly. So that's our first part, is to build this camera. Now, step 2. You need a large but nimble telescope to mount this camera on. The time lapse on the right is approximately over 2 years from a facility in Spain where the telescope mount assembly was constructed. They put it all together, they tested it, and then we had to take it all apart and ship it to our telescope site. If you don't like making the same Lego project twice, this is not the job for you. And on the left, what we see is a highly unique and innovative mirror surface. This mirror, again, a person for size, is 8.4 meters across. It is quite unique in having surfaces of 2 different concavities. There's an outer surface, which is the primary surface, and then there's a changing curvature for the tertiary surface. And usually those are 2 separate mirrors. We would have a normal design of telescopes as a primary mirror, a secondary mirror, and tertiary mirror. By casting the tertiary and the primary out of the same glass, which is something that was not actually possible until recent computerized times, we are able to have a very compact optical design. And what you will look from this telescope, even though it's a very large telescope in mirror size, it is stubby, right? It is very compact. And that is very important if you want to observe quickly. When you want to move fast across the sky, the longer your telescope, the more settling time you have to have after you move it. You have to wait, you take a picture, you move, you want to take another picture, but you have to wait for the whole structure to stop vibrating from the move. And by having a short, compact structure, you can get there much, much faster. In fact, our images are going to be taken every 20 seconds. And there's going to be a few seconds to move, and then another image will be taken again. It's a very, very fast telescope. By the way, the camera that you see here mounted inside the telescope assembly is just a counterweight. It's the real camera has not yet been put on the telescope. Step 3, take all your stuff and take it up the mountain. This is our site at Cerro Panchon on the Chilean Andes in Chile. And this is quite an old drone image of the site, but it's very beautiful, so I decided to use it anyway. This is before the dome structure was erected. You will see the dome structure in later videos. You see tiny little humans for scale. As a software person, I get incredibly impressed by just the sheer logistics of moving stuff across the world and up mountains. On the left, we have an image of the primary mirror that you saw earlier being taken through a tunnel on the way up the summit. It doesn't look so bad here, but it actually got to about a handspan of clearance through the tunnel at one point. And it took a whole night to just get through a 20-meter tunnel. It's very, very slow process to move things up. Now, there is internet up the mountain. We have a 100 gigabit link, actually pretty much all the way from the summit to our North America data centers. However, you can't actually always depend on that internet. Outages happen and so on. And given our influx is central to our observatory operations, it's on top of this mountain, I think somewhere around here, if I remember correctly, in the building, in our 10,000 foot high machine room. So this is, we get the wrong kind of clouds down there. So cloud deployment isn't going to work for us so well. And just to show you a visual aid in what this looks like when you put it all together, you know, you have this large camera, you have this very wide field of view. And what does it look like on the sky? And so here's a pretty semi-artistic image of the sky, but it has the moon on it, which is at least an object we're all familiar with. And here is the field of view of the camera on the sky. So what you see here is every little square is a 4K by 4K CCD. Every 3 by 3 square of CCDs we call a raft. And so the moon does not even fill a whole raft of this image. And this is a single shot. This is a single exposure. And so you can see why this is going to be an unprecedented facility in order to allow us to map the sky quickly. And so once everything is put together, which is something that we are in the process of, then we have a 10-year campaign to observe the sky. And this is useful at both ends. On a nightly basis, you can take an image of the sky, and we can actually, in fact, cover the whole visible sky. We can talk a little bit about what that means twice every week. And that allows you to do very rapid comparisons with how the sky was before and be able to detect things that got brighter or they got fainter or they moved. And this, so for the transient sky, the nightly processing is very important. We have a 60-second budget from the time the shutter closes to get the data to North America, process it, compare it to previous images of the sky, and issue alerts on the positions of any sources that have actually changed since the previous observation. This is a very aggressive schedule. As you follow back and you observe the sky over and over and over again, you can quad your images. It's like HDR. You can kind of stack them together and go deeper and deeper and deeper. And after 10 years of stacking those images, we will have the depths that will allow the cosmologists to make some real progress on the subject of cosmological structure and dark energy. All this data together is a very large camera. You're not going to upload it to Google Photos. It's about 500 petabytes of image sizes at the end of the 10-year survey. And actually just our catalog of sources is going to be 15 petabytes. And we actually have an in-house custom solution for storing those. And what you see here is a simulation from the early days of the project on how we would actually cover the sky. The way you cover the sky, your strategy, your cadence has an effect on the scientific projects. And so people have been discussing on how best to do that for a long time. Remember, you can't beat the laws of physics. So the telescope is in the southern hemisphere, and so you can't cover the northern hemisphere. And of course, you can only see the seasonal part of the sky. You see the winter sky in the winter and the summer sky in the summer. And so what you're doing twice a week is all the sky you can see in a night from your location. But as the Earth revolves around the sun, you're able to fill in that hemisphere And as you progress through the 10-year survey, you will build up quite an extensive map. And finally, you need to get some people, some data centers, and write a whole bunch of software. All our code is open source. We depend on open source. We actually have almost no dependence on non-open source code, with the exception of some vendor code from hardware sensors for the telescope system. And we'd like to give back to open source. So if you are part of the open source community, you have actually contributed to the success of this project. Our original schedule is to go on Sky in 2022. With the pandemic, we have had some delays as our Chile has been on lockdown, but we're hoping to get going not long after that. I'm going to leave you with this beautiful image of the Twilight Sky on Cerro Pachon in Chile. You can see here the dome structure. This is from a picture from last year that my boss took. And I'm going to hand over to Angelo now with this context to tell you how we introduced Influx in this observatory. If there are questions that we can't get to in the Q&A session, otherwise, either because we're out of time, because I talk a lot, or because they're quite complicated to answer concisely, we're going to be hanging out in the Slack, and feel free to drop by and ask us anything you want to know. And I'm going to pass over to Angelo.
All right. Thanks, Frossie, for this amazing introduction. Let me see if I can do this right. Okay. So my name is Angelo. I'm a software engineer for the Vera Rubin Observatory. And I'm an astronomer for training, but what I really like to do is use cool technologies to solve problems. And we have been using InfluxDB for about 2 years now. And I had so much fun. And I also had a great time last year, this InfluxDays at in San Francisco, where I had the chance to meet many of you guys. Okay, let me just try to show my notes here. Okay. Just a second. Okay. All right. So I will start with this image from the sky. Put the and this is just a preview of what our telescope is going to see. And what you see here are galaxies in a small region of the sky, but very, very far in the universe. And because we reach this far, we actually see things when the universe was pretty young, just a few billion years old. But as Frossie said, it's not an easy task to review the universe like this. We will have to map the entire sky from our observatory in Chile, and we need to take thousands of exposures of the sky every night and repeat that for 10 years. And that means about 500 petabytes of data that needs to be processed to detect and measure the properties of all these objects. So that's a very complex computational task. And what's unique about our project is that we are also developing the software to do that. This is the state of the art in terms of data processing in astronomy, and it's all open source software. Our science pipelines They are implemented in C++ and Python, and we have a team of about 100 developers working on this. And they need to instrument the software to make sure that the software is doing the right thing. And here starts our problem. So how to know if the software is doing the right thing, how to define right or wrong, and how to detect performance regressions in the software. If an algorithm is slower or uses more memory, can we easily identify what caused that regression? So those are some of the questions that we need to answer. So performance metrics, they are super important and we have many of them, but let's talk about something different here. Let's talk about science requirements and how they become metrics in our context. So we have science requirements. They guide everything in the project. They fall down to requirements for the construction of the telescope, the camera, the observatory, everything, including the software. Here we have a couple of requirements for the astrometric performance of the telescope. That means how well we can measure the position of objects in the sky. So you see this line here. It indicates the design requirement. We also have a minimum requirement and a stretch goal. And this panel on the left shows how much the actual value deviates from the design requirement. And we developed a software package, which is our verification framework, that translates the science requirements into metrics and specifications. And it allows developers to instrument their code and collect these metrics. So in our context, what a metric definition looks like. So we have a metric name, a description, a unit, and even a reference to the documentation that describes the associated requirement. You can see these metrics here, AM2 and AM3, they are just variations of the AM1 metric, so they inherit most of the AM1 definition. And this is what the specification looks like. It has a reference to the metric name and the values for these thresholds. Okay, so we thought, let's hook our verification framework into our CI system and collect these metrics every time we build our software. And because we run our software on the same test data set, the only thing that changes is the code and the configuration. And if we store these results over time, we can give visibility to our team on what's going on with the software developed. That sounds great. We have this time series for each of our metrics. And from this table here, we can actually inspect the pipeline run that computed these values. Here we have a list of the package that changed since the last build. And so we have an idea of the change in the code that might have caused some of these regressions. That looks great, but this is our in-house solution and it didn't scale for several reasons. First, we start using a relational database, and as you know, relational databases are not optimized for time series data. We got stuck with predefined dashboards and visualizations. The system had some nice interactive visualizations, but was very limited in terms of exploratory analysis capabilities. And our in-house development didn't scale because I was the only person developing the system. Finally, we decided to use our time more wisely and adopt an existing solution instead of reinventing our own. So the first thing was to realize that our problem was indeed a time series problem. And so we started our quest for a time series database. But which one? We see so many solutions out there. We looked a couple of options like Prometheus with Grafana, Honeycomb, Datadog, and InfluxDB. And I still remember what Frossie said to me back then. She said, if it takes more than 3 days to get it working, it's not the right solution for you. And I like to mention this here because it's pretty much aligned with InfluxData commitment to make it easier to work with time series data. And from the options we tried, InfluxDB was really the easiest one to use, and it had all the features that we needed. So we like it. I remember I first used the sandbox option with Docker Compose, and then deployed the Helm charts to have our own instance of InfluxDB. But nowadays is much easier to get started with InfluxDB Cloud. All right. So why InfluxDB? I like to say that it's more than a time series database. It's really an innovative solution to store, process, and visualize time series data. It's also open source. That's really important for us. And it has an amazing community. That makes all the difference. And the fact that InfluxDB has an SQL-like language, it helped to lower the barrier for our users because they already knew SQL. But now, as Chris mentioned, our engineers are learning Flux, and we are very excited about that. Another thing that is really important for us is what I call post-defined visualizations. So our users know better than anyone what needs to be monitored. And with Chronograph, they can create their own dashboards. That's a big change compared to our in-house solution. Creating dashboards is much more dynamic now, and we just leave that to the users. And of course, alert rules and notifications are a big part of that. Exposing the problems on Slack gives visibility and opportunity to everyone in the project to come. All right, so let's talk about our InfluxDB schema design. So this table is a simplified output of the results from one of our pipelines. So the InfluxDB measurement is what groups these results together. The timestamp is usually the time when the pipeline run finishes. We use the tags to store our metadata, and the fields are the metrics that are measured by the pipeline. So yeah, I said that we use tags to store metadata. For example, the name of the data set that we are processing is a good example of a tag. But there's something more fundamental about tags, which is for each combination of tag values, you have a new series. And Paul talked about the series cardinality problem in his presentation yesterday. And I got very excited about the idea of the FluxDB IOX because I think that series cardinality should be a feature, not a problem. For example, let's take a look at this tag called tracked. In astronomy, we represent the sky using a sphere. You have to imagine yourself living inside the sphere, and the sky above you is projected into the surface of the sphere. We divide the sky in these rectangular patches called tracts, and we store metric values per tract in InfluxDB. Depending on the size of the tract, you can have thousands of them. But that's really useful for us because this way you can query metrics and make time series for individual tracks, or you can aggregate the metric values over several tracks, or you can make a snapshot in time and create a metric map to visualize how the metrics change across the sky. Another example of a tag here is the name of the optical filter used at the telescope. So all this is great because with InfluxDB, you can represent other dimensions of your problem using tags. And I'm now looking to InfluxDB IOX, which will be great for this kind of data analytics. So to summarize, in our schema, each point in a series contains the set of metrics measured by the pipeline run, and the results are grouped by the pipeline name. And finally, we can use InfluxDB to track our application metrics. This is an example of a dashboard for one of our pipelines. We have notifications going to Slack. And one feature that's really important for us are the annotations in chronograph. So when you get a notification in Slack, we can go back to the dashboard, add annotations, or we also have weekly meetings where we look at the dashboards and make annotations when there's a metric excursion. As you see here, one example of annotation could be like the ticket number that implemented a new feature in the code, and it's likely to cause the change that you observe. So another quote from Frossie, she says that annotations are more important than the data itself. And that's true because annotations are the human interpretation of the data. And I think I can quote Ryan Betts here from his talk yesterday. He also said, not speaking human language is illogical. And that also applies to annotations. So, right, I'll talk more about annotations later. And I think this concludes the first part of the presentation. And I think that the main take out here is that because we save time using InfluxDB to solve our application monitoring problem, we have time now to get involved in another cool project. And we are going to talk about real-time monitoring of the observatory data. Right. If there's a word to describe the observatory, I think the word is complexity. And I'm not exaggerating here. We really need the real-time monitoring for all the subsystems. We also have requirements to make the historical data available for trend analysis. But the truth is that we need this data. Having this data is crucial. If we don't understand what our system is doing, how can we trust the science that we get from it? So that's the importance of it. And for the observatory data, we have more than 60 different subsystems. We use the RTI DDS as our communication middleware. And there's more than 1,000 DDS topics in the form of commands to control the hardware, events, and telemetry. The total expected throughput from sensor data is about 20 gigabytes per hour. So we easily accumulate 15 terabytes per month. And we expect to have about 1.5 petabyte for the 10 years of operation. And this is just raw data. I will talk later about aggregation and downsampling, which is, I think, the only way to deal with these large amounts of data. So this is the mirror cell, it is the structure that supports the main telescope mirror. And it has these force actuators that are used to compensate the optical surface of the mirror for tiny deformations that happen because of the position of the telescope. So this is the subsystem that produces the highest frequency data with the highest throughput. And we were faced with this problem. Can we record and analyze this data from the mirror cell in real time? So we proposed a solution based on Kafka and InfluxDB. Kafka is used here as a message queue. And as you know, it's designed to guarantee that no data is lost. And another reason for combining Kafka and InfluxDB is the schema management with Avro and the Confluent schema register. We also need the cross-site data replication. And with Kafka, it's easy to write data to other formats, adding different connectors. So for InfluxDB, we use an open source connector from the Stream Reactor project. And we made a few contributions to this connector, like adding support to write arrays in InfluxDB and deal with timestamps in different formats. And one thing that's really important about this architecture is that because the number of topics and subsystems we have to deal with is so large, both the producer and the connector, they have to be dynamic. Dynamic in the sense that if there's a new topic in DDS, the producer will automatically notice that, create the new topic in Kafka, and register the Avro schema in the schema register. And the connector also needs to reconfigure itself to write the data for the new topic in InfluxDB. Right, so the first proof of concept was to characterize the end-to-end latency of this solution, which is essentially the difference between the time we write to InfluxDB and the time that we send the messages. So if we have like a low latency, it means that we can use the system for our analysis. And this is one of the first results regarding the latency characterization. We got like 60 milliseconds, a median latency of 60 milliseconds, and writing about 100,000 points per minute in InfluxDB. And you see it is pretty much stable. No, this test took like one hour. But you see here in the bottom, these bumps that happen when we execute heavy queries at the same time that we are writing data. So the latency increases a little bit, but the good thing is that it recovers later. Right. And the thing is that this system became really useful, and we started using it everywhere. So this is a picture of the mountain in Chile, where you see the auxiliary telescope, the DIM tower, and the weather station tower. So for the auxiliary telescope, back in the lab in August 2019, we had one of the CCDs that Frossie showed for testing at the lab, and we made these dashboards like to monitor the temperature of the CCD. You see that these devices, they have to operate at very low temperature. So here is the like a mean temperature. We have here 6 sensors on the electronic board, and here we have another couple of sensors on the integrated circuit of the CCD. we also made this dashboard to monitor our weather station in the observatory. And one testing here that's super interesting was done before the close down of the observatory because of the pandemic, is the functional testing for the secondary mirror cell. And this is a good example of a dashboard to show how useful a chronograph is for us in this context. So imagine an astronomer testing a subsystem of the telescope for the first time. In this case is the secondary mirror cell. So he needs the ability to create dashboards and visualizations on the fly. It's almost impossible to predict or make these dashboards in advance. So we really use a chronograph as an exploratory tool here. And this dashboard is in particular, it was created by an astronomer at the observatory during the tests, and it uses something that I consider a pretty advanced feature, which is the template variables to create a mapping that has the name of the test as the key and the time range when the test was executed as the value. So we have this nice drop down here from where you can like select the name of the test and you jump straight to when the test happened. And we also use annotations, like manual annotations here. But what we are really excited about is another cool feature that we have been discussing with the design team that will allow us to annotate our time series automatically based on events that we already have. So we have event topics with a message, right? Or with the command to start the test. And we can overlay these events on the top of the time series. And that will be really useful. So this is a picture at the telescope control room. A couple of happy astronomers using chronograph. You can see the dashboards here. And this is how the operation is going to be. So we have an instance. Actually, we already have an instance running at the observatory, but it has a restrict access. Just the observers can use that instance. And we keep data just for 30 days. Then we have to synchronize all this data with another instance running at our data facility here in the US. And this instance will allow access for all the project staff. In addition to that, we have other instances that we call test stands that are in our labs where we test some parts of the telescope. Right, and for this instance at our data facility, we have some additional components. So the first thing is the replicator source connector, which is used to replicate data between the two Kafka clusters. And we decided to implement an aggregator in Kafka using the Faust stream processing library, which is in Python. And the reason we are doing this in Kafka is because we can use we can then use different connectors to write the aggregated stream in different formats. For example, we can write the aggregated stream in InfluxDB. We can write the raw stream or the aggregator stream to Parquet files. And in Parquet files are really useful for our users when they do analysis in notebooks. So they use PyArrow, and then that converts the Parquet to pandas, and then with pandas they can do everything they want. But I think that this aggregator will not be enough. We still have to have multiple retention policies in InfluxDB, and certainly flux tasks to do downsampling and other kinds of aggregations at different levels. So, so this was a project that I work on. Is a Kafka aggregator. We essentially use false agents to compute these summary statistics on these windows of time. And I think a good thing about this architecture is that it scales very well. It scales horizontally. You can add the Faust workers if you have your top Kafka topics with multiple partitions. You can have different agents aggregating each one of the topics, and you produce these aggregated streams. So I think this is like a first step to aggregate the data, and we expect for like the higher frequency streams, like a data reduction factor of about 10. So to conclude, next steps, of course, is the migration to InfluxDB 2.0. We are having like nice conversations with the InfluxData design team about adding annotations to InfluxDB 2.0. So thank you very much for that, for your time to listen to us and implementing these things. Another important aspect is the Flux training for our observatory staff. As I said, we plan on using Flux tasks for downsampling and trend analysis. And we have a lot of work ahead. We just got a contract with Google to move our services to Google Cloud. And the project is in this phase of a transition from construction to operations. So yeah, we see new opportunities for using InfluxDB here. I didn't talk about self-monitoring, but you can ask about that. And of course, as we add more data to our system, we have to deal with the scalability issues and so on. I will let you with some references if you want to learn more about the project. And please, yeah, if you have questions, we are happy to answer. Thank you.
Thank you. There are a couple of questions. Do you have the Q&A, Doc?
Yeah, I got it lined up. So let me fill them really quickly. So Neil Horlock asks, how do you synchronize the clocks between devices? How closely synced do they need to be? That's a really excellent question. So the answer is we're all familiar with the NTP protocol. There's another protocol called PTP, which is the precision time protocol that is used in situations where a higher precision than NTP allows is required. I will say that in optical astronomy, we're actually quite lucky in the fact that we don't have ultra stringent timing requirements. There are other areas of astronomy, like radio interferometry, for example, where if your clocks aren't just all lined up, you don't see anything because you're depending on combining waveforms from different antennas. So yes, it's all about time. And Joel asks, read the annotation slide. Are these annotations automatically created or are they automatically generated? That's also a good question. So currently on our Influx One stack, they are manually annotated. And this is not a use case that's going to go away. Scientists have a meeting together and they kind of huddle over the chronograph dashboard and they go, huh, what happened over there? And somebody says, oh, I know. And then they annotate the point in the series to kind of capture that insight. And this is why I say that these are actually more important than the data, because 6 months later nobody remembers what a spike was all about, and it's actually quite important. The Influx team has been very kindly working with us on an Influx 2 based API that would allow us to also programmatically make these annotations. which would also be terrific. And thanks for all the kind comments in the Slack and in the Google Doc. And it was really nice chatting to you all. And you know, it's very exciting for us to share our journey. And you know, we're hopeful to be back and give you an update in a couple of years' time, maybe.
Yes, and then hopefully some of us can go visit. I think that would be so amazing to see the observatory in person.
It would be great for anybody to go somewhere ever again. Yes.
Awesome. That was phenomenal. I think everybody is just in awe, and we're just so honored that you chose InfluxDB. And actually, I'm actually really pleased that you asked for this feature for this automatic annotations, because I think all of us could actually benefit from this. So thank you so much for that contribution.
Thank you. Thank you for providing great tooling and an open source community that works so well together. Thank you.
Yeah.
Awesome. Thank you very much. Cool. Well, they're both going to be still hanging out in the Slack channel. And then actually Angelo is always in the community Slack channel. So hit him up. He's got now quite a bit of experience with Flux. So if you're new to Flux, you can also ask his opinion.